Okay, so these are papers that Heiko originally posted to the Slack. He posted the neural descriptor fields one, and it uses something called vector neurons as a component thing. And then we talked about this in some detail on Friday at the research meeting. And I thought I'd just summarize it because I think it's fairly relevant, at least to the problems that we're tackling. And at the end, there's a question of, do we want to look into these in more detail or not? I think I will go through it obviously in a much higher level of detail than we did on Friday. And the discussion on Friday was very helpful for me to understand a little bit better. But I'll go into the reverse order of what we did on Friday. So I'll do the vector neurons first. I have maybe 2 or 3 slides on that, and then 2 or 3 slides on this, just describe it at a pretty high level. I'm not going to go into any of the math or the techniques or anything like that. Okay, so vector neurons. So the title is it's a general framework for SO3 equivariant networks. I have no idea what SO3 equivariant meant, so I have to look it up. So SO3 is basically dealing with full 3D rotations. And I'll explain equivariant in a second. And so what they're trying to do is create neurons that work inherently with 3D data rather than 1D vectors of numbers, which is what traditional neural networks do.
So these are not biological vector neurons?
No, it's nothing to do with biology whatsoever.
Yeah.
It's very confusing.
Okay.
So a classical neural network looks like this, where you have a set of numbers. So you have a vector here going to another vector here. So you do matrix multiplication here. Instead, what they have are neurons that are vectors, 3D vectors. So at each point here, you have 3 numbers instead of 1 number. And then they project to a layer of vector neurons where you have 3 numbers again. So these are XYZ initially, and then they can be whatever later, but XYZ numbers coming in. So you have a set of XYZ points coming in that represent the shape of your object, and then it tries to work inherently with this 3D data. So it's sort of groups of 3 neurons, you could think of it that way. And what they're doing in this paper is creating a toolbox for creating all sorts of different deep learning networks that are equivariant to 3D pose and invariant to identity. So I'll explain that in a second. But the point is they're trying to create a general framework so you can create all of the standard deep learning networks that you typically create. You can now create them with 3D pose. And I thought that was a pretty important point so they're focused on this. So what does this invariant equivariant thing mean? So I have a little video here. Let's see if this. So here on the left is a 3D point cloud for an airplane, and on the right is like a representation of what you think it is. And basically, when you have invariance, what you want is
local object pose should not affect the query result.
Okay, so as you move the pose of the object, the identity of the object should be the same, and that's what they mean by invariance. So that's fine.
This property is also desired in a variety of point cloud processing tasks, including classification, segmentation, and surface reconstruction.
Okay, so here they're showing classification, so that's the invariance piece, and the equivariant piece will be shown here. And what they mean is, as you rotate the pose, as you change the pose, there's a corresponding change in the representation. So if you think about a rotation matrix, for example, as you change the 3D angle, it changes in a predictable, known predictable way. And so that's
Is that like just the pose of the object?
No, it can be anything that changes in a predictable way. So
that could be morphological changes or behaviors?
Well, here what they'll show is like here is the segmentation of the object, for example, into wing, body, and all that.
You think about it in terms of coloring the airplane this way. If you rotate it, your coloring should rotate accordingly in exactly the same way.
So for example, if you want the exact shape of the object in the scene, if you want to segment it out, that will change in a very predictable way as you rotate.
Well, I guess what it seems very similar to pose in some sense.
Yeah, yeah.
Oh, I just said, you said no.
No, it's not just pose. Pose is an example.
Pose isn't, these are both examples that pose would qualify for, right? I mean, in a sense.
Well, no, these are not pose.
Well, they, in my mind, they are in some sense. They like.
They're all tied to the pose. But they're
Yeah.
not the
Okay.
pose.
Yeah. If I know the pose, I can generate these.
Exactly. Yeah,
Okay.
yeah,
So so the pose would be the underlying thing that is changing, and then you could generate these objects. These two typical examples would be generated from pose. I have a model of the object, and I know it's pose. I can generate it.
Yeah.
Okay.
Yeah.
I'm not sure if there's other things, like one could argue, if you take a more general case, like you said, like, oh, it could be any behavior or anything, like, well, then I could say the stapler, one might argue that the open and closed state or equivariant parts of the state, because there's a behavior, the movement I do in between that, I don't know if you're making that argument. I don't think so.
So just another example of equivariance, it would just be equivariant to changes in the state.
Yeah, okay, so did they mean it in that way? Did they go that far, or did they just say, no, they're talking about this kind of stuff here?
It's just rotation.
Equivariant is a very generic mathematical thing. So pose is an example of something. The rotation is an example of something that's equivariant, but the exact pixels which belong to the wing would also change in a predictable way with 3D rotation, 3D changes. So these set of pixels that correspond to the left wing here, that change is equivariant to the pose. It's predictable.
I just try one more time. So one of the ideas I'm working on right now is that a model of an object in these different poses is really just, it's a way of representing that. It may not be any different than a way of representing in its different states. And so the question is this trying to deal with all the states of the airplanes? Did they broaden it out to that regard, or all the states of an object, like we were just talking about, or did they just, in nothing, were they just talking about these kind of things, which is really based on pose?
In the experiments that they've tried, it's all rigid stuff.
Okay.
There's no behaviors of objects.
Okay. All right.
They do have a robot grasping thing, which we can get to later, but that's here it's just rigid objects, but there's no particular reason it couldn't be generalized to behaviors.
Okay.
I mean, this notion is very generic.
Well, depending on how they do it, one could be like, oh no, they're just going to do a pose, or they could say, no, this is a really basic algorithm that could do anything. It could show how, objects change.
Well, it's one level more fundamental than that, because they're showing how to create layers of a network that can vary smoothly with pose. And depending on what sort of network you create, you will then be able to apply it to different things.
Yeah. All right.
So it's sort of a toolbox,
Yeah.
if you will. It's not any one thing. It can be used for lots of things. Where you want to treat pose in a kind of a smart way.
Yeah. Again, imagine the airplane has ailerons on the wing and they go up and down. Right?
Yeah.
So it's still an airplane, and it could still be in the same pose, but it would be in a different state. And the question is, does this technique encompass that?
It should, yeah.
It should.
Yeah.
Okay.
I don't see why not. They don't show it in an experiment, but I don't see why it wouldn't be.
Well, okay, I just want to make sure, because it sounded like what you were saying is, if I take the airplane here and I apply transformation where I lift the wing up,
Or tilt the back of the wing up, something like that.
yeah, so I don't think it should be equivariant to something like that. That would be like a change in state, that you can't describe shifting the wing up as rotation of the
It's
entire object.
equivariant to the angle of the aileron.
But that's a specific part of the object. You're not rotating the whole object. This would be,
This is not specific to rotating the whole object.
okay, then I misunderstood.
This example is. And the experiments they tried is, but the generic fundamental technique is not specific to that. It's a generic way of creating a layer that's equivariant to any angle you have that happens to be part of the representation.
Thank you.
So how would I remember the word equivariant?
I think it's an important distinction.
How would you, how do you parse that in your head when you say equivariant? Invariant, I have sort of, okay, right, this is an airplane invariant to its pose, or invariant to its scale, or something like that. That's what we're familiar with. How would you think, what does the term equivariant mean? It means
It varies in a predictable way with what you're equivariant to.
There's a word
It's a mathematical definition.
Okay, I didn't know what the word equiv means. Okay, right.
Yeah, it sort of varies equally.
Okay.
So as you know, if
Okay, it's good enough. Let's keep going.
so, a lot of what we've been talking about would fall under equivariance as well. So their basic trick, the fundamental trick they do is each neuron represents some feature, 3D feature that's like a shape feature, and that's would be normal. The other thing it does is it learns a 3D direction that's specific to that feature. So it learns.
How do three numbers represent a feature? Or is that it's a feature at some position? What is that? A neuron represents a feature, and these are the three attributes of the feature.
It's whatever the network decides to learn.
But as an input, one of those is just a 3D point, X, Y, Z.
Yeah, so XYZ comes in, but it's actually getting XYZ from lots of different points. And then it creates a three-dimensional feature vector. So it could say, oh, I'm in, one way to think of it could say I'm an edge at this orientation.
Okay.
So that could be one, like this could be an edge and this.
I can think of it just classic neural networks, but now it's 3D. Is that
3D,
right?
Yeah. So like this could be, mini column feature. We've talked about the directions of mini columns.
Yeah.
So this could be an example of that. And then what the output of that neuron is how close the input is to that feature in that direction. And every little vector neuron will learn a different direction. So you'll end up with a layer of these vector neurons, each of which represent, the different directions. So you have a smorgasbord of directions and is associated with a smorgasbord of features. And it's going to learn both of those things.
And the tree there is arbitrary, right? Because at some point they no longer represent coordinates. It's not XYZ anymore. So
Yeah. I don't know why it has to be 3 specifically. Yeah. Well, I guess here they're dealing with point clouds, so these directions have to be probably 3D, but that's a question that came to my mind too, like why 3?
You're talking about the features, the
Yeah.
design? Well, it's because I think that's how they check for equivariance, right? Because they apply some rotation to the input, and they should also apply to this, and you should still get the same mapping.
Yeah, but they don't actually, that's just in the proof. They don't actually use that anywhere. That's just to prove that it's equivariant to rotation. But if this was 4 instead of 3, it would probably still be equivariant. And that's what I think is just in the proof that they were showing. And then, well, anyway, they create a layer, and they, like Karan was saying, they prove that these things are equivariant. There's a bunch of other things like normalization layers and other things that they have in here, but this is the fundamental operation that's different.
Is it correct to say that a classic neural network is basically doing a 2-dimensional field, and they do various things with them? And then this is they're just trying to use the exact same techniques, but I the sense that we're dealing with 3-dimensional spaces. Is that all the ways they use neural networks in the past would still work, except now they're inherently 3-dimensional.
That's their claim.
Okay, that's what they're trying to achieve.
Yeah.
I mean, that's an easy way to just explain it, because even in 2-dimensional neural networks, it's very hard sometimes to tell what the neurons mean, right? They're just
The same thing here.
Anything here, you wouldn't know what they
You wouldn't
mean.
know what they mean.
Okay.
The one thing is, you can always use 3D inputs with traditional networks, but you don't get this equivariance property. And that's the big thing that they're doing here, is showing equivariance. Which is, if you want to do anything with pose or recover pose, we need it to be equivariant. And I would say our Monty architecture is equivariant, trying to get equivariant to pose. It falls under the mathematical definition.
Well, because we're trying to make predictions based on the pose.
Yeah.
So if you do this using 2D images and just 2 neurons per vector, would it be equivariant to translation?
Not rotation, not translation.
But those are equivariant to translation.
No,
They're not.
no, just rotation.
This doesn't, oh,
The way they do translation is they just take the center of mass of everything, shift everything, and then they, so the translation piece is hacked.
Also, everything is sensor mass.
is there a convolutional equivalent?
Um,
That you could then wouldn't have to do that?
maybe.
I mean, that would be the way you, I mean, traditional neural networks aren't, they don't take center of mass and center, right?
Well, they don't, they are sensitive to translation, traditional. No.
But if it does, the whole convolutional layer is trying to do is get.
No,
Convolutional layers
very
are
little.
their translation equivariant by design.
It's a little complicated.
Yeah, I thought the whole idea,
Not-
is
not
I could show you a
really.
picture of the dog in different parts and it's gonna recognize it as a dog, right?
Yeah, but it has to be trained in a lot
Dogs in
of,
all
lot of
different parts?
translations.
Really?
Yeah. Yeah. It's only a few pixels translation in Equivariant.
Wow, I didn't know that.
But no, I'm not totally convinced by this. The actual operation of convolution is like you have the same parameters, you just apply them at different places.
Yeah, but there are a lot of edge effects. We can go into this later, but there are a lot of edge effects and things that happen. And so the max pooling, yes, it is to a little bit, but once you get to overlapping things and there are edge effects, it just isn't. That once you get up the hierarchy, it's not.
I think it only works if each filter in your max pooling has some overlap, right? And if that overlap is exceeded, then you lose all track of translation invariance.
Yeah, if you look at like one max pool unit and one set of filter outputs, yes, if you move it a little bit within that receptive field, it's invariant.
That's what I'm thinking.
It's
It's
equivariant.
just a single layer.
Not a layer,
convolutional
a single
layer.
unit. Once you get to the layer, it just isn't. We've done these experiments before, just you don't actually get translation invariance.
Okay, I'm curious to talk about this offline then.
Yeah.
That was, seems like image that works so well. I mean, it's like you'd think like,
You train it on 1.2 million images, and for each image, you have to show lots of distance.
oh, they actually do that.
You manually augment, you manually translate it.
Yeah,
Oh,
and,
my goodness.
and you have to manually rotate it, manually.
I
all sorts
didn't
of
know
things.
that. That's pretty good.
If you don't do that, it doesn't work. So that's an example. You just have to
Okay, so
augment the
this
translation.
stuff is the same problem. In the sense that
Yeah, I mean,
you have to pick the center of the mass. and
you have to
so
pick the center of the mass, yeah.
it's pretty good, yeah.
But it's I think it's a little bit less of an issue here because they're just dealing with positions to begin with. Everything is position based, not color or anything based. It's all shape.
Okay.
I think it's a little bit easier here.
And you don't need to segment the object versus the background. That makes it easier.
Yeah.
You can just subtract the center of mass.
So they create these things which now vary smoothly with pose. And so you can do a lot of things that vary smoothly with pose and don't get confused. And then for recognition for the invariant layers, they have layers that essentially kind of learn to undo this, undo the equivariance and create like a more stable, to think of it as like a pooling layer for in our case. It kind of undoes this. I'm not going to go into the details right now, but they have a invariant version and then an equivariant version. So they're two outputs, which is very similar to what we had in the combs. We had a pooling layer and we had the location layer was in that case, equivariant to translation.
Yeah. Although those, that was never good because when we perceive something, we do perceive it as some more pose. We don't perceive it as just an airplane or just a dog, you know, and we see the details. We also label it as a dog.
Yeah. So here you can read out either one.
Yeah, yeah, but they have a separate undo thing. The thing I'm working on right now is sort of solves this, potentially solves this in a different way, whereas the model of the object is, it's sort of learned through different poses so that you're only recognizing a portion of the model at any point in time, and that portion dictates what the pose is. So the model, it's, again, if you take a 3D, like a cup, and you display it out in a line or a sheet, then you're only recognizing a part of it, and the part, it's all the cup, but the part you're recognizing tells you the pose. So it's a different way of solving the same problem. But anyway, I think
Now there are lots of downsides to this technique too, but anyway, this is,
Yeah.
let me move on. So here's an example of the type of results to do. It's a little bit, so you just look at this top section here. These are theirs, this VN is vector neurons. So they apply it to these two traditional networks.
Are those
PointNet,
3D networks?
those are 3D networks.
Mhm.
The difference here is they have equivariance,
Are those 3D networks, 3D data sets?
3D networks.
Networks.
The data set is this, is it model net or something? It's 40. Huh?
Model net 40.
Model 40. It's 40 categories. These are inherently 3D networks, but they don't have the equivariance property.
Okay.
And so what you see in this pink thing is the first thing here is all the rotations that they were trained with. And the second piece is all the rotations they were tested with. So it was trained with rotations about the z-axis. And here it's tested with all 3D rotations. So it's trying to see how well it generalizes to the other two rotations. And you can see that these other networks, their performance really gets much lower, whereas the vector neuron one, the performance is really not affected by these other two rotations.
So these first two networks did well and they just went around the z-axis. That's
Yeah.
what they were designed for. And then they say, aha, but we'll rotate them otherwise and they fall apart, but we don't.
Yeah, unless you also train them in all sorts of rotations,
Yeah.
which is the last.
Yeah.
column.
If you train it with all sorts, then they get better, but they're still not as good as these guys.
Mm.
But of course, then you have to do a massive amount of training.
Right.
So is there, I read the paper, but I don't remember. Is there any indication of this method requiring fewer rotations than the other methods?
For training, yeah,
Okay.
for training, yeah.
It requires fewer
Well, that was
Much
gonna-
fewer.
I was gonna
That's
say
what this
that.
whole middle column, you only train it on
Z-axis.
z-axis, you don't have to train on the other.
The absolute number, maybe it's just the ZX, but you need like a million.
Yeah, I was gonna say,
That I don't know, my expectation is it still requires a lot of training. That's one of the downsides, it's still a deep learning technique. I have no idea what these
It
other
would make
ones are.
sense if it's less overall, but yeah, it's still a lot less.
So I don't know what these other things are. There's a long list of them. I think this is like another category of stuff, which I'm not sure. But anyway, this is what they show. They also show reconstruction results or prediction. You think of it as prediction. So here's an example of the network that was trained on these airplanes. And if you give it the pose that it was trained on, similar poses, but novel instances, it can reconstruct it just fine. But as soon as you start giving it other rotations, it just falls off a cliff.
Those are the old techniques.
Old techniques, whereas the orange ones, theirs works just fine. It's not affected by the rotations. You can see, a little bit here, for example, but generally they can do prediction quite well on different rotations. In this. Okay,
So that was the first bit.
that was the first paper.
Okay.
Let me move to this other one, neural descriptor fields. So what they do is they create vector neurons, which are now equivariant to pose. Now they actually create object-centric reference frames around objects. And the second big thing they do is they generalize to reference frames of completely novel objects within the same category. And I'll show a couple of examples of
So
that.
what does it mean to create an object into reference frame? Wasn't there an object into reference frame in the previous paper? I mean, you had to pick these dimensions.
No, it's just a classification and that.
But what were the three
reconstruction.
dimensions of space there?
X, Y, Z.
But XYZ relative to what?
I think it was just world coordinates.
Okay, not object coordinates.
No.
So now they're gonna try to do it with object-centric coordinates.
They're going to create a reference frame around the
Yeah,
object.
it's the same idea, but now they're gonna have an object-centric reference frame for X, Y, and Z. Is that?
Yeah,
Okay.
yeah. And one that's works for different objects from the same category. Like different shaped coffee cups.
Yeah.
So I'll show that.
So one of the big problems that we're struggling with here is figuring out what the right, when you're trying to inference, what the right reference frame is, anchoring the reference frame. So it's one thing to say, oh, I got this model of a plane and its own reference frame. But when I infer, I have to figure out what that is, right?
Yeah.
Do they solve that problem?
Yeah.
Or they- Okay. It says given a target pose relative by find the pose in something about two points.
Yeah, so I mean, sort of a one consequence of this is if you give, you can have poses relative to the object, and even if you move the object around, you can still find that pose independent of how that object is related to you. And they use that for gripping. That was the task they turned it on. But the core thing is these two.
Generalized reference. Okay.
So here's an example, coffee cup. So here's a point.
Popular object in it.
Any claim to credit that we got people?
We got the stapler soon.
Yeah. So here's an example. Here's a point that's on this, that's relative to this coffee cup off of this handle. And it gives you some representation at the end of it. And what they're saying is, here's another coffee cup that's smaller and slightly different in shape. You take the same point relative to the handle, and you're going to end up with the same representation. And here's an example.
Was that just scale differences with it?
There's some deformations. It's unclear. That's one of our questions. Unclear how deformable you can be.
Yeah.
Let's see if I can show that video.
What's that thing? Is that supposed to be a gripper? Is that a hand? What is a gripper?
Yeah, it's a hand.
It looks like a hand.
Why is this thing cool?
This is a 2D gripper. The gripper fingers just don't.
Yeah, I'm just thinking, it just, it's funny.
Yeah, sorry, we have to go through.
Yeah, to get to that.
Let's first assume the demonstration and test mugs are identical. We can attach a body frame to the object, record the grasp pose in this frame.
So here they're going to grip it, so now they have the pose of this guy relative to the object in the object's reference frame.
Yeah. So now
And estimate the pose of the mug in its new configuration. The grasp can be executed by moving to the recorded grasp pose, expressed in the new frame. But when the mug has a different shape, this procedure fails. Since the gripper must align to a local geometric feature like the rim, and this feature changes location on the new shape, we must instead attach a local reference frame that moves with the task-relevant feature. Moving to the demonstrated grasp pose, expressed in the corresponding local frame on the new shape, can then align the gripper to the rim.
So that's part of their technique, is they figure out some key features, and they can associate a reference point in the object's reference frame relative to that feature, or near that feature. All they have to do is now locate where that feature is, and then they can, I think.
Well, that makes sense. In some sense, that's what we do too, right? You're going to grab the handle of the mug. It doesn't really matter where the rest of the mug is. You have to figure out where the handle parts are, and then you grab for that.
And the cool thing is they can do this all relative to the object's reference frame, even though kind of the object is distorted up to a certain point. Okay, let me see. Here's an example. Here's like an object that they start with, and they pick a point here on the handle. Now they rotate that. They could find that same point on another object that's rotated differently. And these colors kind of show how the reference frame kind of moves with the object. And they can do it, in this pose, and this larger mug, that pose. Similar thing here with the bowl, I guess.
It's a bowl.
It's a bowl, yeah. So they can basically create these reference frame fields around the object. You can't, it's hard to kind of interpret what it is, but it's something that's invariant to that, rotation.
This is
object
3D,
configuration.
3D facing us, the handle could be.
Yeah.
Yeah, this is in Equivariance we had before, so that this whole field would rotate with the object.
Yeah, I'm just thinking that the example of the cup on the left, they make it see, it looks like it's just rotating in plane, but I assume that's just for visualization.
Yeah,
It could rotate through the plane as well.
Right.
Now, one big disadvantage here is they don't just directly compute things. In order to do this, for every new object and new pose, they have to go through this like minimization process where they try to fit the reference frame to the object, or try lots of different variations to find like the one with the best minimum energy. And so it takes, I'm assuming it's very
That sounds
competition.
like some techniques that you did decades ago. Reminds me of that, where, yeah, you're trying to do stretchy fitting of reference frames,
Yeah,
which can
but
be,
now they're doing it in a deep learning setting. The old ones,
is it slow?
yeah, it's slow. The older ones never work super well,
No.
the template ones. Here, their expectation, I guess, is since it's deep learning, now it's gonna work much better. But yes, it's slow.
The inference is like one optimization of finding the right 6 degrees of freedom reference frame.
Yeah.
Rotation translation. That itself is relatively fast.
But the challenge here,
Okay,
the
so
slow part
I
is,
don't know how fast it is.
the slow part here, you're saying it's a morphing of the shape now, right? It's a
They don't need to morph the shape.
No, it's a different cup, it's a different,
Yeah, it's a different cup, but all they need to find, the cup shape's already kind of represented in the deep learning.
but that was the new novel cup shape that you said was slow, right?
To recognize the post.
Oh, just
So
the
to get
post.
the object-centric thing, yeah.
Oh, I thought it was modifying to the different shape object of slow. You're saying it's the pose that's a slow.
The post pieces, the slow piece, yeah. Sorry, yeah.
So it seems there are like two key things here. One is finding the key points, and that's the whole encoding trend yet, right? And the other being equivariant rotation. That's where vector for me. What about translations? They still do the
same
center
thing,
of mass
same thing,
trick?
yeah.
But then you need to know the center of mass.
Yeah.
So that.
So what they do is they train on 3D point clouds, and they take the center of mass of the point cloud, but they train with partial point clouds. So I think the system will just learn all sorts of different subsets of the object. Yeah, very brute force. Piece of brute force. Okay, so I'm just kind of summarizing and nothing. So I'm using your same format I grew up, but I changed the words a little bit. So it's a toolbox for 3D invariant and equivariant network layers. That's the vector neurons thing. You can represent the 3D location in full 3D pose anywhere in the reference frame of the object. Represents the full morphology of complex objects. So they show like rabbits and things like that, including local curvatures, just learns all that stuff. It can work with some deformation of 3D shape. We're not really sure how deformed it can be or how different. It can work with partial 3D data, like I was saying, because it's sort of brute force trained on partial 3D data. And it generalizes to novel instances, but it's not really clear how novel it can be. But it's a general technique with 3D data. It is not specific to vision. This just requires 3D points. There's no color, no nothing in here. You know, presumably it can be augmented with color, but the core thing is not specific to vision. It's really unclear how it scales to large numbers of objects. The last one I showed, I think they only tried on 3 different objects.
Right.
There's how well it deal with noise and ambiguity is not clear. It's not really clear if the exact pose can be recovered. It's just you get to a representation that's the same as it would be, but it's not clear you can read it out that it's, you know, 2 degrees this way, 20 degrees that way. Training is probably quite slow, and inference may be slow as well. It's sort of unclear to me exactly how we might or might not want to use it in Monty. Maybe individual modules could use these tools, and these are maybe each module could have something like these vector neurons or something that's equivariant. That's the base of it. We might be able to remove some of these limitations. I guess a question here, should we even investigate this or not? As I was about to leave this morning, the way, if you think about the columns paper, it occurred to me that we could even do something similar to the columns paper, just replace this location signal with their signal. Because we never really had an object-centric location signal before. And so that's one possible way to approach this. Obviously, this is very tied to the Monty architecture, but this one simple way to think about it is we just change the location signal with this representation. Again, I don't know that any of this would work in our context or not, but that's sort of occurred to me as I was leaving the
Yeah,
door.
and another thing you could change instead of the location, instead of the sensory input. If you look at it, this gives you some way to describe in an equivariant way the local curvature.
The local shapes, yeah.
Yeah, the local
Yeah. So it might be some replacement for this as well. But it doesn't have color or, those kind of things would still.
As a field, is this new and hot, or is this something that's been around for a while, or? What's
This paper is what?
December last year in archive.
Okay, December, so that's new paper. In the previous paper, is that recent too?
Yeah, it's last year, I think April or March.
Is this like generating huge amounts of buzz, or lots of people working on this? Do we know that or not?
Didn't it get a best paper award at the conference it was presented at?
I don't know what best paper, but they got it moral.
I think Jack and Neurons has quite a bit of citation for it. The first paper.
I don't know what the number of citations.
It was 14 essentially.
For you, 1 year.
I guess the reason I asked that question is, how many people are working on this right now? Is it 20 people? Is it 200 people? 2,000 people? I mean, it's like, it makes a difference because if there's a lot of people working on this idea, there'll be a lot of progress in going forward. Or it could be just, it could be an idea that, hey, this is really cool, and then it doesn't go, reminds me a little bit of, like an example of that would be some of the SLAM architectures, which are hot, and then they kind of disappear,
Let's take a guess at this, Jim. There's another paper a year before this called Geometric Deep Learning, which introduced this whole approach to constructing architectures with different types of invariances and equivariances. And this strikes me as a special case of that kind of program. And the geometric deep learning thing did make a pretty large splash. So my guess is that this is one example of introducing those. It's a special instance of creating a network with certain types of invariances or equivariances that we'll see a lot more of them in the next 10 years.
No problem. That's good. I mean, one could say, hey, maybe all neural networks are going to go in this direction because the entire field of AI is going to have to be built on concepts of.
It's hard to say.
This could be, replacing. This could be infused through everything, right? Because the world has to go to 3D sensory motor modeling, and this could be the basis for doing that non-artificial neural networks. Or it could be just the subfield that's interesting. We don't have to know the answer.
One area I've been talking to Scott Purdy a lot, who's at Zoox in self-driving. So there they deal with point clouds constantly, and so they use a precursor to this. I could see in the self-driving world they could gravitate to these kind of networks.
Slow inference? With the slow inference?
I mean, it needs to be sped up, but.
You mean just, I think.
Again, no one would use exactly this technique, right? This is going to evolve. This is just, deep learning is evolving so fast.
But the idea that you're infusing 3D dimensionality into the networks in an inherent way is a big deal, right? Because that's.
That they're already doing in self-driving cars. They use the precursor to this called point nets, which deal with 3D points. The new thing here is the equivariance piece.
Yeah. I mean, because in some sense, our whole thing is like, hey, sensory motor learning is all about 3D space and all about modeling and 3D structure and how those structures are morphed and so on. And that really hasn't been the center of neural networks for a long time. So it should be moving in this direction. One thing, interesting question, one thing I've always felt like if we could define what a learning module has to do in Monty and just say, here's what its inputs have to look like, here's exactly what its outputs have to look like, and these are the things it has to be able to accomplish, then that would maybe help answer your question. Is like, well, given I have to do these things, is this going to help me do them or not? Could I have one team just goes off tries to do it using these techniques? Another thing.
Well, I don't using these techniques, we can only specify it at a very generic level. We can't say it has to be exactly this or exactly that, because these things are just going to learn these representations, and it's really hard to specify ahead of time. I mean, it may be that we can recover the exact pose, for example. Right now, we'd have to do some work to actually get it to correctly output the correct pose, right? But we could say, the representations of the pose have to be consistent for consistent poses. We could say it at that level,
I guess maybe,
which might not help.
yeah, I know, maybe I'm being too simplistic, maybe my understanding is not deep enough, but I'm just thinking like, hey, in my mind, there should be a specification what a learning module has to do in Monty. And in some ways, we're somewhat indifferent to how you go about doing that, right? And maybe some things can be better than others. But I've always said, if you can define the interfaces, then you can have at it in between. So I don't know.
But I don't know if we can do it at the level of Monty modules. I mean, it would be like the entire hierarchy would be this. That's what I mean.
Well, we could define a single learning module and say, could this be like a single? Well, I'm just throwing that as an idea.
Yeah.
Yeah, I think that's a good point. To be clear about what does it exactly do. I mean, we could say we wanted to recognize a certain object and a certain pose. And you would expect each module, each column would recognize the object.
Well, there's still the training scenes, you have to manipulate these objects or turn them or rotate them, right? So there's still
yeah. Well, you don't have to rotate them too much because it's sort of equivariant the rotation. You just have to show it in lots of, subsets or weird deformations.
well, it's like anything. It's like I can't, this won't, if I can't see the bottom of the airplane, I won't be able to recognize them.
You have to do it at that level.
You still have to move things around, and that's true for us, and that's true for this, right? So,
But you wouldn't have to do the 2D rotations, and you would only have to show the other side, for example, if it's, or maybe 3 or 4 angles at it.
yeah, well, that's okay. Like that too, right? So
this relates to another question I had. Why do you say training is slow? Like, do you have specific numbers or something? Because it should be fast based on what you just argued.
Yeah, it sort of gets back to what Lucas was saying.
Yeah,
I should verify this. I just assumed it. My intuition was similar to, I think, what Lucas was saying. You just have to show a lot of partial subsets of these point clouds, and
a single image presentation could be lots of training. So.
yeah.
I read this paper too, I think they were very vague about how the encoders train. And it seems to me that the encoders require a lot of training just on that.
And these are complex networks, like, it might be.
Yeah, there's also two different papers, right? So for the second one, it will be much more training data intensive and time intensive for the training. And then I think even for the 3 objects, you need like 100,000 examples and train on that one. The vector neuron piece is relatively simple.
But the second one, they don't even talk about training encoder. They just assume you have a training encoder.
Yeah, they need
There's this open question
exactly,
how hard it is to train that encoder.
Yeah, they need an encoder plus then on top of that the training vector.
Yeah, we could try, Heiko, what you're saying is, each module will recognize full objects anyway. And maybe we could just try potentially small modules at the level, looking at small patches.
Yeah.
And see if.
Getting a local shift features. That's one representation.
I mean, the thing is, all this stuff we've been discussing about curvatures and smooth surfaces and displacements and all that stuff, it's already sort of captured in here. We wouldn't need to do any of that stuff. Don't need to build a graph. It sort of incorporates all that.
But it's an alternative, right?
It's an alternative.
We could still go 2 parallel paths and combine them both.
It's a very different mentality than what we've been talking about. All right, so that's, I don't know, should we spend time on this or not?
What's your intuition saying?
I think we should spend a little bit of time on this. Yeah. It's so close to what we're trying to do. Getting some more intuition, like there's so many unknowns here. Maybe it fits very well into Monty. We could at least go that far and see, does it fit well, and can we specify some sort of an interface?
and possibly some variation.
Some variation.
You tweak a little bit. And
Yeah, what I was thinking in terms
Yeah,
of
yeah.
variation, so instead of having this encoder network that maps the whole point cloud into some making representation of the thing which we take off the shelf, we have multiple of those local descriptors around the object, and sort of multiple of those local curvatures, and sort of do one local curvature relative to the others.
Yeah.
Encoded that.
Yeah, each one could have a little reference frame associated with it, and then you could build a graph from that, I guess.
The key thing about Mani is not, it's not like, oh, we have to have many learning modules, or we have to do this. Basically, it's a platform for sensory motor learning. And there's some capabilities we want to be able to do with sensory motor learning and sensory motor interaction with objects in the world. And so, it's hard to know, like, oh, could you plug in a wholly different type of learning system that sort of achieve the sensory motor learning aspects that you want to achieve? I think the trick is to, if you're going to investigate this, it could become the tail that wags the dog, right? You don't want to just run it and become, then you just become doing this, you know what I'm saying? We don't want to lose sight of what the bigger picture we're trying to achieve is. And
That's the issue, yeah.
yeah, so I think that's the problem. That's always the risk of working on something like this. Is that, we just say, oh, let's just investigate this, as opposed to thinking, what we're trying to achieve overall. Does it help us do that? But anyway, it sort of seems, like you don't want to discount it. It seems pretty important, a significant, potentially significant addition to neural networks.
Yeah, we could try just for feature learning, local curvatures, and see how this would go. It would be learn equivariant curvature features. Maybe that's the start.
Yeah,
And that would be- yeah, that's a good.
it's a good idea.